Okay, so here we have the wave again, increment delta x, and the increment on the wave up here. We enlarge this increment so that we can draw it here. So here's the increment of the wave, and this increment is going to be along a slope which is equal to the partial of y with respect to x, because the slope is the the derivative of the y function with respect to position. And that's fairly straightforward. The velocity of this wave is partial y with respect to t at that position at whatever time. Now also we have tension F. Okay, we have the tension in the string, so we have a tension vector F, which is parallel to the segment, parallel to the increment as it actually appears on the wave. So that now we know, well, what we know, and I'm not going to go into the detail of this, you can review this, it's a first semester topic, but the power is going to be equal to the dot product of the force with the velocity. Okay, and if somebody really wants me to review that, I'll do a quick video on it, but power is going to be the dot product of the force with the velocity. So we have this picture, we have this force here, we have this velocity here, this tension force here, this velocity here, and we want to find the dot product. Well, what's the dot product? Well, the dot product, again, this is a first semester topic, it's basic vectors, but the dot product is going to be the product of the projection onto this vector of this vector with this vector. So we project the F vector over here to do the dot product, and we have this vector, the projection vector, and this vector, and we do the product of these. And we do have to watch the signs. We have to see whether this one's in the same direction or opposite direction as this one, if the projection is in the same or opposite direction to the velocity. Okay, so we have this. So here's our power. Now let's look a little more closely at the projection of the F vector. Okay, so here we got the F vector. It has an X and a Y component. Should be clear that we're referring to the sides of this triangle, but just to be sure, we'll kind of draw those in. The Y component, of course, is the projection onto V of the vector F, because the V vector is in the Y direction. And then we have the X component. Well, the Y component divided by the X component is just the slope. And the Y component, of course, is the projection. What do we know about the slope at this point? Well, we know that the slope is the partial of Y with respect to X. So a small slope, for small slope, we have, first of all, okay, well, let's talk about small slope for a minute. We're exaggerating the Y coordinates here. These displacements are small, and the slopes of the actual string are small slopes. Okay, they're not nearly as big as we've depicted them. For small slopes, we know that fx is going to be about equal to f. In other words, fx being the f times the cosine of this angle. If this is a small angle, the cosine is very close to 1, so that fx is practically equal to the hypotenuse here. Fy over fx is the slope. Small slope, fx is approximately equal to f. So the projection of v on f is approximately equal to what? Well, it's approximately equal, get some white chalk here, approximately equal to the slope times f. But what's the slope? The slope is partial of y with respect to x. So this projection is f times a partial of y with respect to x. So now what we have here is we have f partial of y with respect to x times the partial of y with respect to t. I say you got to watch the signs here, making kind of liberal use of the notation, but that all gets taken care of here. In the case that we see here, where the velocity is down and the force is in this direction, partial of y with respect to x will be positive, partial of y with respect to t will be negative, and we're going to have a negative product at this point. Okay? Well, in any case, this shows you that the power then is the F dot V. It's F times partial y with respect to x times partial y with respect to t. And from what we saw previously, I guess we need to make that connection. We'll do that in a minute. This is equal to the expression that we got previously, so let's flesh that out. Okay, I've filled this in, but let's just look. We got F partial y with respect to x, partial y with respect to t. What's partial y with respect to x? What's partial y with respect to t? Well, y is presumably a sine of kx minus omega t, and we don't know what omega is, but we assume we know what omega is, and we assume we know what k is, so that the partial y with respect to x, just by the chain rule, gives you ka times the cosine of kx minus omega t. Now, I'm not going to write out the kx minus omega t to preserve space or to conserve space, but that's what's going to go inside of these parentheses at any point. And partial y with respect to t for this function would actually be negative omega a times the cosine of kx minus omega t. So that we plug those in for partial y with respect to t, partial y with respect to x. I said those backwards. Well, we get the f. We get a k from here. We get an omega from here, and it's going to be a negative omega. And we're going to get an a from each of these, so we're going to have an a squared, and we're going to have a cosine from each of these. So we're going to have a cosine squared of, if you want to write it out, kx minus omega t. And then, let me pause and write this down. Okay, I've written some stuff out. I also made a correction down here. I wrote something ignorant. First of all, we got the k here, and we're going to express this k in terms of omega and c, c being the speed of the wave, so that we can get, we're going to do that. Okay, so k, well, c is omega over k. You can review that. Think about what omega means, what k means. We get k equals omega over c, c being the square root of f over mu. Reciprocal c is going to be the square root of mu over f. So k is omega times the square root of mu over f. So we replace k by omega square root of mu over f. And then we do a little bit of simplification. We got the f square root in the denominator divides into the f in the numerator. Let's make sure that the camera's down low enough to see that. And gives us a square root of mu times f. That should be straightforward. The omega times the omega gives us an omega squared and an a squared. And then we have this cosine squared, but we know that the average value of cosine squared over any whole number of cycles is 1/2. Since we're talking about a wave with a large number of cycles, we can safely say that the average value of the cosine squared of kx minus omega t is going to be 1/2. And you should review how to integrate that and just why the average value of the cosine squared is 1/2. Very important quantity. Same true for the sine squared. In any case, the average value of the cosine squared is 1/2, so that the average value of the power is 1/2 square root of mu f times omega squared a squared, which is the same expression that we got previously just by looking at the maximum kinetic energy of an increment and extending that over time.